The universe once seemed silent and unchangeable, a perfect dome of fixed stars. Then a star exploded in the daytime sky, proving the heavens were alive with violent change. This video reveals 25 celestial events that transformed our understanding of space and time, from that ancient supernova to the first sound of colliding black holes. By the end, you will see the cosmos not as a static backdrop, but as a dynamic story where each chapter rewrites the rules of reality. We will uncover how a comet's predictable return cemented the rule of law in the cosmos, and how a faint microwave whisper confirmed our universe's fiery birth. These are not just discoveries, they are moments that shattered our deepest assumptions. What does our endless curiosity about the stars reveal about us? A brilliant new star blazed in the sky one morning in the year 1054. It was not a distant, twinkling point of light, but a beacon that shone even in broad daylight. A celestial visitor so unexpected it was recorded with awe by court astronomers in China and the Islamic world. For 23 days, anyone on Earth could look up and see this profound change written across the heavens. That star was not being born, it was dying in the most spectacular way imaginable, a supernova. Its shattered remains form what we call the Crab Nebula, a cosmic cloud that is still racing outward 1,000 years later. This single event shattered a 2,000-year-old idea, the belief that the stars and planets were perfect, unchanging objects fixed to crystal spheres. The universe, it turned out, was alive with drama and violence. The death of that star did more than just create a beautiful nebula. It forged the very elements that make up our world, seeding the cosmos with the building blocks for future planets and for life itself. At the heart of that expanding cloud lies another marvel, a pulsar, a city-sized spinning ball of pure neutron star that ticks with the precision of a cosmic clock. How would your understanding of reality shift if you saw proof that the cosmos itself is being constantly remade? This was the first crack in the perfect celestial sphere, a revelation that our universe is a place of dynamic and violent creation. Nearly 5 centuries after that first recorded supernova, the heavens staged an even more defiant performance. In November 1572, a star in the constellation Cassiopeia ignited with such ferocity that it outshone the planet Venus, a brilliant pinprick of light visible even at noon. Among the many who gazed up in wonder was the Danish nobleman Tycho Brahe, an astronomer with a meticulous mind and a nose made of brass after a duel. He did not merely watch this new star, he measured it with an unprecedented precision for his time, night after night, tracking its position and its slow fade over 16 months. His crucial finding, published in a book titled De Stella Nova, was that this star showed no parallax. What does that mean? As Earth moved in its orbit, this new star did not shift its position relative to the background stars. This simple, careful observation proved the object was not a nearby atmospheric phenomenon, not a comet, but was located far beyond the Moon, deep in the realm of the so-called fixed stars. This was an intellectual earthquake. For nearly 2,000 years, Western science had rested on the Aristotelian idea that the heavens beyond the Moon were perfect, immutable, and eternal. Stars were unchanging points of light fixed to crystal spheres. This new star, this stellar nova, was a blatant crack in that perfect celestial sphere. It was a change, a violent and brilliant transformation happening in a place where change was thought to be impossible. Tycho's supernova did not just add a new star to the sky, it tore a hole in the philosophical fabric of the universe. It forced thinkers to confront a startling new reality. that the distant heavens were just as dynamic and subject to birth and decay as our own imperfect Earth. The courage to publish these findings, to challenge a dogma that had governed human thought for millennia, helped shatter the authority of ancient texts and paved the way for a new kind of science, one built on observation and measurement rather than pure reason. That single point of light in Cassiopeia illuminated the path for all of modern astronomy, proving that to understand the cosmos, we first had to accept that it could change. The perfect, unchanging heavens had been proven a myth, yet Earth still held its privileged place at the center of everything. That final bastion of cosmic vanity would soon fall, not to a brilliant explosion, but to a quiet man peering through a tube of glass. In January 1610, Galileo Galilei aimed his newly improved telescope at the bright planet Jupiter. He saw it not as a simple point of light, but as a small disk, and beside it, he noticed 4 tiny, star-like points arranged in a straight line. He assumed they were distant stars, but the very next night their positions had shifted. Night after night he watched, meticulously recording a celestial dance. All 4 points moved, but they never strayed far from Jupiter, some passing behind it, others in front. Galileo had made an astonishing deduction. These were not stars at all. They were 4 moons orbiting the planet Jupiter itself. This was a revelation that shook the foundations of human self-importance. For over 1,000 years, the geocentric model, the idea that every celestial body revolved around the Earth, had dominated Western thought. Yet here was direct, visual, undeniable proof of celestial bodies orbiting something other than our world. The cosmos was not a series of perfect crystal spheres centered on humanity. Jupiter was its own center of motion, a miniature solar system with its own attending worlds. Galileo's discovery of Io, Europa, Ganymede, and Callisto was a fatal blow to the Earth-centered universe. It provided the strongest evidence yet for the Copernican model, which placed the Sun at the center, and it suggested a radical new idea that the laws of physics governing our world might be the same everywhere. If moons could orbit Jupiter, then Earth itself was just another planet orbiting the Sun, a single world among many. Suddenly, the universe felt vastly larger and more impersonal, yet more knowable. The true power of this moment was not just in what Galileo saw, but how he saw it. He did not rely on philosophy or ancient texts. He used a new technology, an instrument that extended human senses beyond their natural limits. His telescope revealed a hidden reality that had been invisible for all of human history, waiting just beyond the reach of the naked eye. If a simple arrangement of lenses could unveil such a profound truth, what other cosmic secrets remain hidden, waiting for the right tool or the right question to bring them into view? Galileo's telescope had revealed a cosmos far more complex than anyone dreamed, yet it was still a place of unpredictable wonders. Then came a different kind of mystery, a ghostly traveler that appeared without warning, a comet blazing across the night sky in 1682. Most saw it as a terrifying omen, a sign of divine displeasure or coming disaster, but one man saw a pattern. The astronomer Edmund Halley delved into historical records and noticed something extraordinary. The paths of this comet and those seen in 1531 and 1607 were strikingly similar. He proposed a revolutionary idea that seemed almost heretical. What if it was not 3 different comets, but one single object traveling on a vast, elliptical loop around the Sun? Using his friend Isaac Newton's new laws of universal gravitation, Halley performed a monumental calculation. He plotted the comet's path and made a stunning prediction. This same comet, he declared, would return in the year 1758. For the first time in history, a celestial event was not just observed, it was foretold. The stage was set for a cosmic test of human reason. When 1758 arrived, astronomers across Europe trained their telescopes on the predicted patch of sky. And right on schedule, the comet reappeared, a shimmering vindication of Newtonian physics. The object that once inspired dread was now proof that the universe operated on knowable, mathematical principles. Halley's Comet, as it was forever named, was not a mystical portent but a predictable member of our solar system, a celestial body governed by the same gravitational law that holds you in your chair. This was more than a successful prediction. It was a profound shift in our relationship with the cosmos. The heavens were no longer a realm of capricious gods, but a grand, ticking clockwork. Can you imagine the awe of that moment, watching a prophecy of pure mathematics blaze into reality in the night sky? This predictable visitor had cemented the rule of law in the heavens, proving that through reason and observation, we could not only understand the cosmos but anticipate its motions. The predictable clockwork of Halley's Comet had revealed a solar system governed by law, but the stars themselves remained distant, fixed points of light. For 300 years since the time of Copernicus, the final proof of an Earth in motion had remained frustratingly out of reach. Astronomers knew that if our planet truly raced around the Sun, the nearest stars should appear to wiggle slightly in the sky over the course of a year, an effect called stellar parallax. It is the same illusion you see when you hold a finger up and view it with first one eye closed, then the other. Your finger seems to jump against the background. But for all those centuries, not a single star could be seen to budge. The failure to detect this shift was a powerful argument used by those who clung to an Earth-centered universe, suggesting the stars were so impossibly far away that their motion was undetectable, or worse, that the motion did not exist at all. Then, in 1838, the German astronomer Friedrich Bessel took on this centuries-old challenge. He focused his telescope not on a bright, famous star, but on a faint, fast-moving pair called 61 Cygni. For over a year, with painstaking patience, he measured its precise position against the backdrop of more distant stars. His reward was a number, a tiny angular shift of just 0.314 arcseconds. To grasp how small that is, it is like measuring the width of a coin from 30 miles away. That almost imperceptible wobble was everything. It was the first direct, concrete, and undeniable proof that Earth was not the stationary center of creation, but a moving platform orbiting the Sun. The heliocentric debate, which had begun with Copernicus and been fought for by Galileo, was finally settled, but Bessel's measurement did something even more profound. That tiny shift was a cosmic ruler. By applying simple trigonometry, Bessel calculated the distance to 61 Cygni. The number was staggering. The star system was over 66 trillion miles away. To make sense of such an immense void, astronomers soon began speaking in terms of light years. The distance light travels in 1 year. 61 Cygni was 10.3 light years from Earth. The light entering Bessel's telescope had begun its journey a decade before he was even born. In an instant, the universe expanded from a relatively cozy solar system to a realm of almost incomprehensible emptiness. The nearest stars were not just far, they were isolated islands in a vast, dark ocean. We were not merely a planet orbiting a star. We were inhabitants of a tiny oasis in a cosmic desert of staggering scale. What does this immense distance say about our place in the universe? It is a humbling reminder of our solitude, but also a testament to our curiosity, that from this small world we could reach out with mathematics and measure the abyss itself. Bessel had used mathematics to measure the staggering emptiness between the stars, but the power of calculation was about to perform an even greater magic trick, conjuring a new world into existence before a single telescope had even seen it. The story begins not with a discovery but with a problem. The planet Uranus, discovered by William Herschel in 1781, was misbehaving. Astronomers tracking its path around the Sun found that it was straying from its predicted orbit, as if being gently tugged by an unseen hand. For decades, this wobble was a nagging inconsistency in the otherwise perfect clockwork of Newton's universe. Could Newton's law of gravity, so successful here on Earth and with Halley's Comet, be flawed at the edge of the solar system? In the 1840s, two brilliant mathematicians, Urbain Le Verrier in France and John Couch Adams in England, attacked this puzzle independently. They both turned the problem inside out. Instead of assuming the known planets were the only gravitational influences, they postulated an eighth, unseen planet beyond Uranus. They then used the mathematics of Newtonian mechanics, working backwards from the observed irregularities in Uranus's path, to calculate the precise mass and orbital position this hidden world must have to cause such a disturbance. It was an audacious feat of pure reason, a celestial detective story where the crime was a gravitational tug and the suspect was entirely theoretical. Le Verrier sent his final calculations to the Berlin Observatory. On the night of September 23, 1846, astronomer Johann Gottfried Galle pointed his telescope to the exact spot in the constellation Aquarius that Le Verrier's numbers dictated. There, within 1 degree of the predicted position, was a faint blue-green disk that was not on any star chart. They found it. The planet Neptune, a world 4.5 billion kilometers away, had been discovered not by chance but at the tip of a pen. The impact was immediate and profound. This was the ultimate validation of Newtonian physics. The same force that made an apple fall on Earth could, from across the solar system, guide a mathematician's hand to a new planet. The universe was not just knowable, it was predictable in the most spectacular way. A hidden reality had been revealed not by a better lens, but by the sheer force of human intellect and calculation. How powerful is a theory that can point to a new world with nothing but paper and ink? This mathematical conquest affirmed that the cosmos operates on a set of reliable, universal rules, and that we, with our curious minds, are capable of deciphering them. If mathematics could reveal an entire planet, what other invisible forces and unseen worlds might still be hiding in the numbers, waiting for the right mind to find them? Newton's clockwork universe, so beautifully confirmed by Neptune's discovery, seemed to have one final, unshakable foundation: the force of gravity itself. But in the mind of a quiet patent clerk, a revolution was brewing. Albert Einstein proposed that gravity was not a mysterious, instantaneous pull across empty space, but a curvature, a warp in the very fabric of space and time caused by mass and energy. Imagine the universe not as a static stage, but as a vast, flexible trampoline. Place a heavy bowling ball in the center, and the fabric stretches and dips. Roll a marble nearby, and it will curve around the depression, not because of a magical force, but because it is following the contours of the bent surface. This was general relativity, a theory so radical it suggested that even light, traveling in a straight line, would have its path bent when passing near a massive object like the Sun. For years, it remained a beautiful but unproven idea, a set of equations waiting for a cosmic experiment. That experiment arrived with the total solar eclipse of May 29, 1919. On that day, the moon would perfectly block the sun's brilliant face, revealing the background stars in the daytime sky. Sir Arthur Eddington led 2 expeditions, one to the island of Principe off the coast of Africa and another to Sobral in Brazil. Their mission was perilous and precise: to photograph the star field around the darkened sun and compare it to photographs of the same stars taken at night months earlier. If Einstein was right, the sun's immense gravity would act like a lens, subtly shifting the apparent positions of those stars outward, making them appear slightly farther apart. The weather was treacherous, with clouds threatening to ruin everything. But as totality began, the clouds parted just enough. The teams captured their glass photographic plates, fragile records of a moment that would redefine physics. Back in London, after months of careful measurement, the results were announced. The starlight had been bent. The measured deflection matched Einstein's predictions almost exactly, while it was twice what Newton's theory would have allowed. The news swept across the world, catapulting Einstein to instant global fame. A headline in the Times of London read, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." This was not merely a new fact, it was a new reality. Gravity was not a force but geometry. Space and time were not absolute and rigid. They were a dynamic, malleable substance woven together into a single entity called spacetime. The eclipse provided the first direct evidence for this new cosmic architecture, a framework that would later become essential for predicting black holes, gravitational waves, and the expanding universe. It showed that our most fundamental intuitions, even those defined by Isaac Newton, were not the final word. What other truths about the nature of reality feel completely solid to us today, yet might be waiting for their own eclipse to reveal their hidden flexibility? Einstein's new cosmos was curved and dynamic, but one question still loomed. Was this grand structure of space-time eternal and unchanging, or did it have a story? The answer came not from a philosopher's speculation, but from a former boxer and lawyer turned astronomer, peering through the most powerful telescope on Earth. Perched atop Mount Wilson in California, the 100-inch Hooker telescope was a marvel of its age, and Edwin Hubble used it to stare into the heart of faint, cloudy patches known as spiral nebulae. For years, astronomers had debated their nature. Were they nearby clouds of gas within our own Milky Way, or were they something else entirely, something staggeringly distant? Hubble focused on a special kind of star within the Andromeda Nebula, a Cepheid variable, whose rhythmic pulsing allowed him to calculate its true distance. The number he found was breathtaking. Andromeda was nearly 1 million light-years away, far beyond the borders of our own galaxy. In an instant, the universe exploded in size. Our Milky Way was not the entire cosmos. It was just one island universe among countless others, each a swirling metropolis of billions of stars. The loneliness of our position, first hinted at by Bessel's measurement, was now absolute. But Hubble did not stop there. He began measuring the light from these newly discovered galaxies, and he noticed something peculiar. Their light was stretched, shifted toward the red end of the spectrum. This redshift was a cosmic Doppler effect, the same phenomenon that makes a siren's pitch drop as it speeds away from you. Nearly every galaxy he examined was flying away from our own. And the most astonishing part was the pattern he uncovered. The farther away a galaxy was, the faster it was receding. This relationship, now called Hubble's law, painted a startling picture. The entire universe was expanding like dots on an inflating balloon, all growing farther apart as the space between them stretched. This was the final death blow to the idea of a static, eternal cosmos. The universe was not simply existing, it was evolving. It had a history. If everything is flying apart now, then running the cosmic film backward in time implies there was a moment when all matter and energy were compressed into an unimaginably dense, hot point, a beginning. Hubble's discovery was the first observational clue that would lead directly to the Big Bang theory. We live not in a fixed arena, but within an unfolding story, a cosmos actively growing larger and colder with every passing moment. How does it feel to be a part of something that is not just vast, but also in a state of constant, majestic flight? The expanding universe was no longer just a theory, but it lacked one final piece of empirical proof. Where was the heat from that initial fire? That proof arrived not through a grand astronomical quest, but as an irritating hiss in a giant radio antenna. At Bell Labs in New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting their sensitive new horn antenna. They were plagued by a persistent, faint microwave signal that came from every direction in the sky, day and night. It was an annoying background noise they could not eliminate. They scrubbed the antenna clean of what they jokingly called a white dielectric material, which was essentially pigeon droppings, but the hum remained. This was not a technical glitch, it was a whisper from the dawn of time. Unbeknownst to them, a team at Princeton University had been building a detector specifically to find this signal, a predicted remnant of the universe's hot, dense beginning. When the two groups connected, the stunning truth was revealed. That irritating hiss was the cosmic microwave background, the cooled and stretched afterglow of the Big Bang itself. After 13.8 billion years of cosmic expansion, the searing heat of creation had cooled to a faint whisper just 3 degrees above absolute zero, permeating all of space. This was the smoking gun. The universe did indeed have a fiery, explosive origin. For the first time, we could observe the infant cosmos directly. This fossil light shows us the universe as it was just 380,000 years after its birth, a time before stars or galaxies, when space was a hot, opaque plasma of particles and light. The most striking feature of this ancient light was its profound uniformity. It arrived from every corner of the sky with nearly the same temperature, painting a picture of a remarkably smooth and homogeneous early universe. Yet, buried within that smoothness were the tiniest of fluctuations, minute variations in temperature 1 part in 100,000. These tiny ripples in the fabric of the early cosmos were the gravitational seeds from which everything we see would eventually grow. Every galaxy, every cluster, every vast cosmic web of dark matter, all originated from those infinitesimal imperfections imprinted on the first light. This discovery transformed cosmology from a field of grand speculation into a precise observational science. We are now bathed in this ancient radiation, the oldest light in existence, a direct window into the primordial moment. What other secrets about our ultimate origins are still encoded in that faint cosmic echo, waiting for a more sensitive ear to listen? The cosmos had revealed its birth cry, but its graveyards held even stranger secrets. A few years after the echo of the Big Bang was identified, a young graduate student named Jocelyn Bell Burnell was meticulously analyzing reams of paper rolling out from a new radio telescope in Cambridge. Her eye caught a curious signal, a persistent rhythmic pulse arriving every 1.337 seconds with such unwavering regularity it seemed artificial. It was too perfect, too clock-like to be a natural phenomenon. In a moment of scientific whimsy, the source was half-jokingly labeled LGM-1 for little green men. The idea of an interstellar beacon from an alien civilization was a thrilling, if unsettling, possibility. But the truth, once uncovered, was even more extraordinary. These were not alien signals. They were pulsars, the spinning corpses of massive stars that had died in supernova explosions. A pulsar is a neutron star, a city-sized object containing more mass than our Sun, crushed into such incredible density that a single teaspoon of its material would weigh billions of tons. As this remnant spins, powerful beams of radiation shoot out from its magnetic poles, much like the sweeping light of a cosmic lighthouse. From our perspective, each rotation brings a beam into view, creating the perfectly timed pulse that so captivated Jocelyn Bell Burnell. This discovery was the first direct confirmation that neutron stars, a theoretical prediction for decades, actually existed. They were a new, exotic state of matter, a realm where atomic nuclei are packed together shoulder to shoulder, governed by the bizarre rules of quantum mechanics under gravitational forces beyond comprehension. These celestial metronomes became unparalleled natural laboratories. Their precise ticks allowed physicists to test the limits of general relativity with a new level of accuracy. The discovery of the first binary pulsar in 1974, two of these dense stars orbiting each other, provided the first indirect evidence for gravitational waves. As the pulsars spiraled inward, their orbital decay matched exactly what Einstein's equations predicted, energy being carried away by ripples in spacetime itself. Pulsars demonstrated that the death of a star was not an end, but a transformation into something profoundly strange and powerful. What other bizarre stellar corpses, invisible to our eyes, are silently ticking away in the void, their rhythmic beats tracing the intricate geometry of spacetime? For centuries, the moon was a symbol, a perfect silver disk in the sky. That abstraction ended when a human hand reached down and scooped up a handful of lunar dust. Between 1969 and 1972, the Apollo astronauts did more than plant flags and take photographs. They collected rocks. They brought back 842 pounds of another world, turning the moon from a distant light into a tangible place we could hold in our hands. Scientists eagerly cracked open these pristine containers of lunar regolith, and the stories they told were explosive. The most fundamental revelation was the moon's age. By analyzing radioactive isotopes in the samples, they could perform a kind of cosmic clockwork, dating the formation of the lunar crust to around 4.51 billion years ago. This was not just a number for the moon. It gave us for the first time a solid lower limit for the age of our own planet and the entire inner solar system. We now knew with certainty that our world was a veteran of billions of years of cosmic history, but the lunar surface told another, more violent story. It was scarred with craters, and the rocks revealed that this pummeling was not a slow, steady rain, but a cataclysmic storm. The evidence pointed to a period scientists call the Late Heavy Bombardment, a time around 4 billion years ago when asteroids and comets rained down across the inner solar system. The same violence that carved the moon's great basins, the Maria we see as dark patches, also ravaged the young Earth. This was a paradox. This cosmic artillery barrage coincided with the very first whispers of life on our planet. Did these impacts deliver the water and organic molecules that made life possible? Or did they sterilize the planet over and over again, forcing life to cling on in the most desperate refuges? The moon, a silent witness, had recorded a chapter of solar system history that Earth's active geology had long erased. The Apollo missions left more than footprints. They left behind small arrays of mirrors called retroreflectors. Even today, observatories on Earth fire laser beams at these mirrors, timing the light's round trip. This laser ranging provides the most precise measurements of the moon's slowly increasing distance from Earth, and it continuously tests the predictions of Einstein's general relativity with stunning accuracy. Holding a piece of the moon is to hold a piece of our own deep past, a relic from a time when the solar system was a chaotic shooting gallery. How does it change you to know that the silent orb in your night sky is not a stranger but a sibling bearing the scars of a shared violent childhood? The silent, dusty plains of Mars suddenly felt much closer in July 1976. That summer, a robotic geologist named Viking 1 settled gently onto the rust-colored soil, followed months later by its twin, Viking 2. These were not mere flybys or orbiters. They were the first functioning laboratories ever placed on another world, and their primary mission was audacious: to search for signs of life. For the first time, humanity was not just staring up at the red dot in the sky, it was reaching out to touch it with a specific, profound question: are we alone? The landers extended their robotic arms, scooped up samples of the fine Martian soil, and delivered them to a suite of 3 miniature biological experiments inside their bellies. Each test was a masterpiece of engineering designed to detect the metabolic processes of Martian microbes. One experiment, labeled the labeled release, added a nutrient soup to the soil and watched for the telltale gas that would signal something was eating it. Astonishingly, the result was positive. A gasp of gas was detected, a flicker of potential biology. For a moment, it seemed we might have an answer, but science demands more than a single clue. The other experiments told a more complicated story. A second test designed to find organic molecules, the fundamental building blocks of life as we know it, found nothing. It was utterly barren. The Martian soil was a chemical desert, devoid of the carbon-rich compounds that litter every inch of our own planet. How could there be life without any of its essential ingredients? The initial excitement gave way to a deep and lasting puzzle. The prevailing explanation became that the Martian soil was not biological, but intensely chemical. The soil was likely full of powerful oxidants, like hydrogen peroxide, created by the relentless barrage of solar ultraviolet radiation on the thin atmosphere. These compounds would have broken down any organic material over millions of years, and they could also mimic life by reacting violently with the nutrients in the experiment, producing that tantalizing but false positive. The Viking missions did not find life, but they transformed Mars from a world of canals and fantasy into a real place. They gave us our first detailed weather reports from another planet, documenting thin winds and temperatures far below freezing. They analyzed the atmosphere and showed it was overwhelmingly carbon dioxide. They photographed a stark, rock-strewn landscape under a pinkish sky. This was not a dead Earth, it was a different kind of world altogether, one with its own harsh and reactive rules. The legacy of Viking is not a failure, but a recalibration of our entire search for life. It taught us that the universe is not obligated to follow our assumptions. The question shifted from a simple "are we alone" to a much deeper inquiry. What does life actually look like in an alien environment, and are our tools even capable of recognizing it? That first ambiguous handshake with Mars set a challenging standard, proving that the greatest discoveries often begin not with answers, but with better, more complicated questions. The search for life on Mars had ended in a profound and humbling ambiguity, proving that the universe does not easily yield its secrets. Yet, just 2 decades later, a discovery was made far beyond our solar system that would redefine our very concept of a world. In October 1995, 2 Swiss astronomers, Michel Mayor and Didier Queloz, announced a finding that seemed to defy both logic and our own solar system's blueprint. They had found a planet orbiting a star called 51 Pegasi, a star remarkably similar to our own Sun. The planet, named 51 Pegasi b, was a gas giant with about half the mass of Jupiter. But its orbit was insane. This colossal world was not circling in a stately, years-long path like our own Jupiter. It was scorchingly close to its star, completing a full orbit in just 4.2 Earth days. A year on this world passed in less than a week. How could such a thing exist? The astronomers did not see this planet directly. Its presence was inferred from a delicate, rhythmic wobble in the light of its parent star. The gravity of the orbiting planet pulls the star back and forth, ever so slightly. As the star moves toward us, its light is compressed, shifted slightly toward the blue end of the spectrum. As it moves away, the light is stretched, shifting toward red. By measuring this subtle stellar dance, Mayer and Queloz could detect the invisible planet's mass and orbit. This discovery of the first exoplanet around a sun-like star was a seismic event in astronomy. It shattered the long-held assumption that our solar system was a standard model for the cosmos. Suddenly, planets were not rare curiosities. They were everywhere. This single detection opened the floodgates to a new field of science, exoplanetology. We now know of thousands of these distant worlds, and they come in a staggering variety. There are hot Jupiters like 51 Pegasi b, boiling in their close orbits. There are super-Earths, rocky planets larger than our own. There are water worlds, lava planets, and planets orbiting two stars at once, just like Tatooine from science fiction. The question is no longer whether other planets exist, but what kind of strange and wonderful environments they possess. The search has now sharpened its focus, moving from finding any planet to finding that specific, precious kind, a rocky world orbiting within its star's habitable zone, where temperatures might allow liquid water to pool on the surface. The discovery of 51 Pegasi b did not just add a new entry to a catalogue. It transformed our galaxy from a collection of lonely stars into a universe positively teeming with worlds. How does it feel to look up at the night sky now, knowing that nearly every point of light you see likely hosts its own family of planets, each with its own unique story? That brilliant flash of a new world had revealed a galaxy full of planets, but the death of a star would soon offer a far more intimate lesson in cosmic life cycles. In February 1987, a star simply catalogued as Sanjalik-69202 met its end. It detonated in the Large Magellanic Cloud, a small satellite galaxy orbiting our own Milky Way, and for a few glorious months, it became the brightest supernova seen from Earth in nearly 4 centuries. This was Supernova 1987A, a celestial gift that arrived at the perfect moment in human history. For the first time, our global network of telescopes and detectors was sophisticated enough to capture every facet of a star's death throes. The light itself was a spectacle, but the real revolution arrived 3 hours before that visible flash. Deep underground, in massive water tanks designed to detect the most elusive particles in the universe, instruments registered a fleeting burst of 24 neutrinos. These ghostly particles, produced in the star's final, catastrophic core collapse, had streamed across 160,000 light-years of space, passing effortlessly through planets and people to deliver their message. Their detection was a monumental confirmation of supernova theory. We had not just seen the star die, we had felt the shudder of its heart giving way. As the light from the explosion expanded, it did something even more dramatic. It lit up a series of mysterious rings of gas that the star had puffed off in its old age, creating a celestial hourglass that glowed for years. These were not just a beautiful accident, they were a fossil record. The rings showed us the final, turbulent acts of the star's life, long before the main event. It was like watching a flashbulb go off in a dark room, suddenly illuminating the entire history of the space. Supernova 1987 became the most important stellar laboratory we have ever had. It allowed astronomers to test and refine every model of how massive stars live and die. By watching the expanding debris cloud and the fading light, they could precisely calibrate the cosmic distance scale, using this one cataclysm to better measure the vastness of the universe. We learned that the star that exploded was a blue supergiant, not a red one as most theories had predicted, forcing a welcome and humbling revision of our textbooks. This single event connected the dots between theoretical physics, neutrino astronomy, and traditional observation. It demonstrated that a star's death is not an isolated event, but a transformative process that seeds the galaxy with heavy elements and energizes the gas from which new stars will one day form. The iron in your blood and the calcium in your bones were forged in an explosion just like this one long ago. So what can the death of one star tell us about the life cycle of all stars? It tells us that we are all, quite literally, stardust, the temporary assemblage of atoms that were once blasted across the cosmos in a brilliant final farewell. There is a profound power in staring into nothing. In December 1995, astronomers did exactly that. They pointed the Hubble Space Telescope at a patch of sky near the Big Dipper that was, by all previous accounts, utterly empty. It was a void, a blank space between the stars, chosen specifically because it was thought to contain nothing of interest. For 10 full days, Hubble's giant eye remained locked on this single, dark point, its shutter open, collecting the faintest trickle of photons that had traveled across billions of years of expanding space. This was a gamble, a massive investment of precious telescope time that could have yielded nothing but a black photograph. The result was not a void. It was a universe in overdrive. The Hubble Deep Field image revealed a tapestry of light, a crowded metropolis of nearly 3,000 galaxies. Each of those smudges of light was not a star, but an entire galaxy, a swirling collection of billions upon billions of suns, each with the potential for its own planets and possibilities. And this incredible cosmic crowd was crammed into a view that covered an area of the sky smaller than a grain of sand held at arm's length. If that tiny, seemingly empty spot was so packed with galaxies, then the entire canopy of the night sky must be an almost solid fabric of them. This single image transformed a theoretical estimate into a visual, visceral reality. The observable universe, it implied, was not just vast but overwhelmingly populous, containing perhaps 100 billion galaxies. But the deep field was more than a census, it was a time machine. Because light takes time to travel, the fainter, redder smudges in the image were not just far away, they were from the deep past. Hubble had captured a core sample of cosmic history, showing galaxies in their infancy, some as they were just a few 100 million years after the Big Bang. We could see them in their chaotic youth, colliding and merging, their shapes distorted and irregular, slowly evolving over billions of years into the majestic spirals and smooth ellipticals we see in our cosmic neighborhood. This long stare into the void did not reveal emptiness, but a universe overflowing with structure and story. That single image answered one question about the scale of the cosmos, while raising 1,000 more about the journey of its inhabitants. Does the sheer abundance of galaxies make our own Milky Way feel less lonely, or does it amplify the silence, suggesting that in a cosmos so crowded, the real mystery is not the number of worlds but the quiet between them? The Hubble Deep Field revealed a universe overflowing with galaxies, all rushing away from one another in the aftermath of the Big Bang. Every cosmologist assumed they knew the next chapter of this story. The mutual gravitational pull of all this matter, all those galaxies and the vast webs of dark matter between them, had to be acting as a cosmic brake, steadily slowing the expansion over billions of years. The only real question was whether this deceleration would be enough to one day reverse into a big crunch, or if the universe would simply coast toward a slow, cold halt. Then, in the late 1990s, two teams of astronomers set out to measure this expected slowdown by using the universe's most reliable mile markers, a special class of stellar explosion called Type Ia supernova. These supernovae are thought to always explode with the same intrinsic brightness, making them perfect standard candles. By carefully measuring how much dimmer they appeared from vast distances, scientists could precisely gauge how much the universe had stretched since the light began its journey, effectively measuring the expansion rate across cosmic time. What they found was not a slowdown, it was the opposite. The most distant, ancient supernova were fainter than they should have been. The data pointed to a staggering conclusion. The expansion of the universe was not slowing down at all. It was speeding up. Something was forcing space itself to stretch at an ever-increasing rate, overpowering the collective gravity of everything. This discovery was so shocking and counterintuitive that the teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, spent months checking and rechecking for errors, from interstellar dust to the possible evolution of the supernova themselves. But the result held. The universe's expansion is accelerating. This revelation completely overturned the standard model of cosmology and earned the researchers the Nobel Prize in Physics in 2011. The cause of this cosmic acceleration was given a name: dark energy. It is not a substance we can touch or see, but rather a property of space itself, a mysterious repulsive force that makes up about 68% of the entire energy content of the cosmos. Think of it like this: if the universe is a loaf of raisin bread baking in an oven, gravity is the dough itself, trying to pull the raisins closer together. Dark energy is the yeast, causing the entire loaf to expand at a faster and faster rate, ensuring the raisins will never meet again. This means the ultimate fate of the cosmos is not a fiery crunch or a slow freeze, but a gradual and relentless dissipation. Galaxies will be pushed beyond our cosmic horizon, their light forever too faint to ever reach us again, leading to a future of cold, dark isolation. The discovery of dark energy was a profound humiliation for physics. It showed that the universe is dominated by components, dark energy and dark matter, that are completely invisible and unknown to us. We can only infer their existence through their gravitational effects. All the stars, planets, and galaxies we see are just a mere 5% of the total cosmic budget, a visible froth on a deep, dark ocean of mystery. What does it mean for our quest to understand reality, that the fate of everything is being driven by forces we cannot see, touch, or even begin to comprehend? That faint cosmic hiss, the echo of the Big Bang, was just the beginning of the story. The true plot was hidden in its subtle imperfections, and to read it, we needed a map of the infant cosmos. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, was our first dedicated cartographer of creation. For 9 years, it scanned the entire sky from a quiet gravitational point a million miles from Earth, measuring the cosmic microwave background with a sensitivity that would have been unimaginable to Penzias and Wilson. Its successor, the European Space Agency's Planck satellite, followed with even sharper eyes, mapping the ancient light in exquisite detail. The images they sent back were not simple pictures of noise. They were cosmic baby pictures, speckled with a pattern of tiny temperature variations, hotter red spots and cooler blue spots, differing by mere millionths of a degree. These minute fluctuations were not random. They were the gravitational seeds of everything to come, the blueprint for the entire large-scale structure of the universe. By analyzing these patterns with the precision of a forensic scientist, cosmologists could extract the universe's vital statistics with stunning accuracy. The data confirmed the universe is 13.8 billion years old, a number now known with a certainty of less than 1% error. It precisely measured the composition of the cosmos: 27% dark matter, 68% dark energy, and a mere 5% ordinary matter, the stuff of stars, planets, and us. One of the most profound revelations was the geometry of the universe. The patterns in the microwave background showed that on the largest scales, the universe is geometrically flat. This is not flat like a tabletop, but flat in the sense that parallel lines never meet, and the rules of Euclidean geometry we learned in school hold true across the cosmos. A flat universe was a key prediction of a theory called cosmic inflation, a mind-bending idea that in the first trillionth of a trillionth of a trillionth of a second after the Big Bang, the universe underwent a violent, exponential growth spurt, inflating from a subatomic speck to a volume larger than our observable horizon. The patterns WMAP and Planck saw were exactly the kind of magnified quantum ripples such an event would produce. These missions transformed cosmology from a field of elegant speculation into a hard precision science. We were no longer just guessing about the universe's origins, we were reading its birth certificate, a document written on the sky itself. The faint spots in that map are the primordial overdensities where gravity began its patient work, pulling matter together over billions of years to form the first stars, the galaxies, the clusters, and the vast cosmic web we see today. Your existence and the existence of every galaxy was encoded in those microscopic wrinkles in space-time. How does it feel to know that the entire complexity of the cosmos was preordained by a pattern finer than a fingerprint, imprinted in the first flash of light? Einstein's cosmic symphony had been silent for a century, a mathematical prediction waiting for an instrument sensitive enough to hear it. On September 14, 2015, that instrument finally listened. The twin laser interferometers of the LIGO Observatory, separated by 1,900 miles, registered a vibration so minuscule it defied belief, a shift in spacetime 1,000 times smaller than the nucleus of an atom. For 20 milliseconds, a gravitational wave passed through the Earth and through us. The signal was a rising chirp, a cosmic melody encoding a catastrophe that occurred 1.3 billion years ago when two black holes, each about 30 times the mass of our Sun, spiraled into each other in a final, frantic dance. In the last fraction of a second, they merged into a single, more massive black hole, converting a quantity of mass equivalent to 3 suns directly into pure energy in the form of these gravitational waves. The power released during that instant outshone every star in the observable universe. This was not a flash of light or a burst of radiation. It was a shudder in the geometry of reality itself, a ripple in the fabric of spacetime predicted by Einstein's general relativity in 1916. For the first time, we did not just see the universe, we heard it. This single detection opened an entirely new sense for astronomy. Light can be blocked or absorbed by dust and gas, but gravitational waves pass through everything virtually unimpeded. They carry information about the most violent, dark events in the cosmos, collisions, explosions, and mergers that are often completely invisible to traditional telescopes. That first chirp did more than confirm a theory. It provided the first direct, unequivocal evidence that binary black hole systems exist and that stellar mass black holes themselves are real, physical objects. We were no longer inferring their presence from the way they made nearby stars wobble or from the X-rays of hot gas falling in. We were listening to them die. Since that first detection, gravitational wave astronomy has blossomed into a new field. We have now heard the collisions of neutron stars, events that also flash with light, allowing us to witness the forging of heavy elements like gold and platinum in real time. We have detected the ringing of newborn black holes as they settle into their final, smooth form. Each event is a new note in the symphony of spacetime, a direct probe of gravity in its most extreme regime. We have moved from being passive stargazers to active listeners of the cosmos. What other dark, massive events are constantly shaking the fabric of our reality, their silent songs still waiting for our next, more sensitive ear to arrive? For a century, black holes existed as pencil marks on a page, the ultimate triumph of mathematics over imagination. They were predictions, cosmic phantoms defined by their profound absence. Then, on April 10, 2019, a phantom gained a shadow. The Event Horizon Telescope collaboration unveiled the first direct image of the supermassive black hole at the core of the galaxy Messier 87, a gravitational monster weighing 6.5 billion times more than our Sun. This was not a picture of the black hole itself, for a black hole, by its very nature, emits no light. It is a one-way door from which not even light can escape. What we saw was its silhouette, a dark central shadow encircled by a brilliant, lopsided ring of fire. This ring is the photon sphere, the point of no return where light is bent into a perfect circle by the black hole's immense gravity, a whirlpool of superheated gas and dust spiraling inward at nearly the speed of light. The asymmetry of the ring, brighter on one side, is a direct result of the relativistic Doppler effect, the gas on the side spinning toward us blazing brighter as its light is boosted, while the receding side dims. Every detail of this image was a test. The size and perfect circularity of that shadow matched the predictions of Einstein's general relativity with stunning precision, confirming the theory in the most violent gravitational arena nature can provide. To capture this image of a target the size of a donut on the Moon, astronomers had to build a telescope as large as the Earth itself. They synchronized a global network of 8 radio observatories, from the high deserts of Chile to the volcanic peaks of Hawaii, creating a single, planet-sized instrument through a technique called very long baseline interferometry. The coordination was a monumental feat of international cooperation, requiring exquisitely precise atomic clocks and weather conditions to be perfect at every site, all at the same time. The data collected was so vast it could not be sent over the internet. It was physically shipped on half a ton of hard drives to central processing centers. This was not a single snapshot, but a painstaking reconstruction from countless observations, a digital echo of a cosmic roar. Seeing the unseeable does more than confirm a theory. It changes our relationship with the cosmos. It transforms an equation into an environment, an abstraction into a destination. That iconic orange ring gave a face to the void, making one of the universe's most enigmatic objects feel startlingly, undeniably real. How does it feel to look into the abyss and see it looking back, not with an eye, but with the precise, beautiful geometry of a law we can finally see in action? While black holes revealed the geometry of cosmic emptiness, a different kind of hunt was underway to understand the very substance of existence. Deep beneath the French-Swiss border, inside a 17-mile ring of supercooled magnets, physicists were chasing a ghost. For decades, the standard model of particle physics had been our most precise map of the subatomic world, brilliantly predicting the behavior of quarks, electrons, and the forces that bind them. Yet this elegant theory had a gaping hole. It could not explain why the fundamental particles had mass at all. Without mass, particles would simply zip through the universe at the speed of light, never coalescing into atoms, never forming the stars, planets, or people that make up our tangible reality. The universe would be a sea of ethereal, weightless energy. The proposed solution was as strange as it was beautiful, a theory suggesting that all of space is filled with an invisible, molasses-like field, the Higgs field. Just as a person wading through water moves more slowly and appears to gain inertia, particles interacting with this field would acquire mass. The different strengths of these interactions would explain why an electron has a tiny mass and a top quark a much larger one. But a field is an abstract concept. To prove it existed, scientists needed to find its signature, a ripple in the field that would manifest as a particle, the Higgs boson. To create such a ripple required recreating energies not seen since the universe was a trillionth of a second old. The Large Hadron Collider at CERN was the machine built for this purpose, smashing protons together at nearly the speed of light in a subterranean cathedral of science. For years, the colossal detectors ATLAS and CMS sifted through the debris of billions of collisions, searching for the unique, fragile fingerprint of the Higgs. Then, on July 4, 2012, the announcement came. A particle consistent with the Higgs boson had been observed. The discovery was not a flashy explosion, but a statistical peak in a mountain of data, a whisper of a signal emerging from a blizzard of background noise. This was the final, missing piece of the Standard Model. Its confirmation was a monumental triumph of human prediction and perseverance, validating a 50-year-old theoretical vision. Finding the Higgs boson did more than complete a puzzle. It answered a profound why. It explained the origin of mass for the building blocks of our world, providing a mechanism for how a universe of pure energy condensed into the solid matter we see today. This connection ties the quantum world directly to the cosmic scale, for the properties set by the Higgs field in the first instance after the Big Bang determined how galaxies could later clump together under gravity. How does it feel to know that the very mass that gives you weight, that allows you to feel the ground beneath your feet, is granted by a silent, invisible field that permeates the entire cosmos? This discovery marked the end of one great chapter in physics, but in doing so, it opened the door to an even deeper mystery, the nature of the dark universe that lies beyond our current understanding. The final frontier of our solar system was once a blank space on the map, marked only by a single, blurry pixel named Pluto. For decades, that was all we had, a faint smudge of light that represented the edge of our known planetary family. Then, in July 2015, that pixel blossomed into a world. NASA, a New Horizons spacecraft, raced past at over 30,000 miles per hour, and in a breathtaking flyby, it revealed Pluto not as a dead ball of ice, but as a stunningly complex and vibrant planet. The images that streamed back were nothing short of revolutionary. Here was a landscape of soaring mountains, not of rock, but of solid water ice, hard as granite in the deep cold. Vast plains of frozen nitrogen spread out like glacial fields, flowing slowly over eons. A hazy, blue atmosphere clung to the small world, creating stunning silhouettes against the distant sun. This was not the inert fossil we had imagined. Pluto was alive with geological activity, a small, distant body with a surprisingly dynamic heart. The discovery forced a complete rethink of what it means to be a planet. How could a world so far from the sun's warmth possibly generate the energy to reshape its own surface? The answer likely lies in heat from the slow radioactive decay of elements deep in its core, or perhaps in the strange antifreeze properties of ices at profoundly low temperatures. Pluto was telling us that even in the deepest freeze, worlds can remain active, holding secrets we never thought to look for. But the mission was not finished. On New Year's Day 2019, New Horizons performed another first, flying past a small, enigmatic object in the Kuiper belt named Arakoth. If Pluto was a mature, complex world, Arakoth was its ancient ancestor, a primordial relic preserved in the deep freeze for over 4 billion years. Its shape was the most startling reveal of all, a flattened snowman composed of 2 distinct lobes gently fused together. This was a contact binary, a direct fossil from the solar system's dawn. Arakoth's pristine, untouched appearance provided the clearest visual evidence yet for a theory of planetary growth called hierarchical accretion. It showed that planets did not form from violent, chaotic collisions, but began with a gentle dance. Small particles of dust and ice slowly coalesced into smaller bodies, and those bodies, over millions of years, gently, slowly merged together at walking speed, building larger and larger planetesimals. Arakoth is a snapshot of that very process, a moment frozen in time just as two separate objects decided to become one. These twin flybys did more than just explore two specific objects. They opened a window into the earliest chapters of our solar system's story. The outer darkness is not a barren wasteland, but a cosmic attic filled with the preserved building blocks of planets. Every icy body drifting in the Kuiper belt is a time capsule, holding chemical and geological records of conditions from a time before the planets even finished forming. We are no longer just looking at points of light. We are reading the first pages of our own origin story, written in ice and rock at the very edge of the light. What other primordial secrets are locked in that deep freeze, waiting for the next robotic messenger to decode their ancient language? Gravitational waves had given us ears, but we were still straining to see in the dark. Then, on August 17, 2017, the cosmos offered a symphony for all our senses. The LIGO and Virgo observatories felt the distinct, rising chirp of space-time ripples, but this signal was different. It lasted for 100 seconds, far longer than the fleeting shudder of colliding black holes. This was the spiraling dance of two neutron stars, the ultra-dense corpses of long-dead suns, circling each other in a final, fatal embrace. Within 2 seconds, NASA, a Fermi satellite, detected a powerful burst of gamma rays from the same patch of sky. The silent tremor of gravity had been accompanied by a flash of light. An alarm bell rang across the global astronomy community. For the first time, we had a coordinated alert. Dozens of telescopes, from massive radio dishes in Chile to the Hubble Space Telescope in orbit, swiveled to pinpoint the source. They found it in a faint, distant galaxy known as NGC 4993, 130 million light-years away. What they witnessed over the following days and weeks was a cosmic forge in action. A new light bloomed in that galaxy, a kilonova, its color shifting from blue to deep red as the expanding cloud of material from the collision cooled. This was not just a light show, it was the answer to a millennia-old mystery. For decades, we had wondered where the universe's heaviest elements like gold, platinum, and uranium were created. Ordinary stars and supernova could not account for them. The unique signature of the kilonova's light revealed the truth. In the extreme, neutron-rich environment of that collision, atoms were ripped apart and reassembled in a process called rapid neutron capture, forging these precious heavy elements in vast quantities. The calculations were staggering. That single event likely produced an amount of gold equal to several times the mass of our entire planet, scattering it across the galaxy. The platinum in a wedding ring, the uranium in a power plant, all of it was forged in such a violent, stellar collision billions of years ago. This event did more than just trace the origin of our jewelry. It provided a powerful new cross-check on the cosmos. By comparing the distance measured from the gravitational wave signal with the redshift of the host galaxy, astronomers could calculate the expansion rate of the universe in a completely new way, independent of supernova or the cosmic microwave background. The dawn of multi-messenger astronomy had arrived. We were no longer just seeing the universe or just hearing it. We were doing both at once, like suddenly understanding a movie with the sound turned on. Each cosmic messenger, gravity and light, told a part of the story, and together they revealed a narrative of creation that was richer and more complete than we ever could have imagined from one sense alone. How many other cosmic stories are being told right now? Their full plot only understandable when we learn to listen and watch at the very same time. A new kind of explorer now flies where no spacecraft was designed to go, diving directly into the atmosphere of a star. NASA Parker Solar Probe, launched in 2018, is a mission of audacious extremes built to withstand temperatures that would vaporize almost any other object. In December 2021, it achieved the impossible, becoming the first human-made object to officially touch the Sun, not by landing on its surface, but by flying through the superheated outer atmosphere known as the corona. The probe did not melt. It sailed through a region where the Sun's magnetic influence becomes absolute, a place where the solar wind is born. The data it sent back was revolutionary. It revealed that the solar wind is not a smooth, continuous flow, but is structured by sudden, violent kinks like magnetic switchbacks. These are sharp reversals in the magnetic field that whip particles outwards, accelerating the wind to tremendous speeds. The probe also found evidence for the origin of this acceleration, pinpointing tiny, frequent explosions known as nanoflares. These are miniature solar flares that constantly erupt across the Sun's surface, collectively pumping enough energy to heat the corona and power the relentless solar gale. This solves a profound mystery that has puzzled scientists for decades. The Sun's visible surface is about 10,000 degrees Fahrenheit, but the corona above it soars to millions of degrees. It is as if the air in a room became thousands of times hotter than the fire in the fireplace. Parker is showing us that this counterintuitive heating is likely driven by the relentless energy of these nanoflares and the tangling and reconnecting of magnetic field lines. This is not just an academic puzzle. The Sun's activity is the engine of space weather. Violent eruptions from the corona can send massive clouds of charged particles toward Earth, creating beautiful auroras but also posing a severe threat. A powerful solar storm could potentially cripple satellites, knock out power grids, and disrupt global communications for weeks or even months. By understanding the fundamental processes within the corona, we learn to predict these solar outbursts, protecting the technological backbone of our modern civilization. The Parker Solar Probe is in essence sampling the very heart of our solar system's engine. What it learns about our own Sun provides a template for understanding the billions of other stars in our galaxy, each with its own corona and stellar winds. This daring journey to touch a star is rewriting the textbook on stellar physics, proving that sometimes the greatest mysteries are not in the farthest reaches of space, but burning brightly in our own celestial backyard. The Hubble Deep Field had already stretched our minds to their limits, revealing a universe crammed with galaxies. Yet that profound view was still a portrait in visible light, a story with its earliest chapters missing. In July 2022, a new eye opened in the void and it saw in heat. The James Webb Space Telescope unveiled its first deep field, focusing on a patch of sky known as SMACS 0723. What appeared was not just a cluster of galaxies, but a gravitational lens, a natural magnifying glass where the immense gravity of the foreground cluster warps and amplifies the light from far more ancient objects behind it. Webb's infrared vision pierced through veils of cosmic dust that had blocked Hubble's view, capturing the faint, stretched light of galaxies whose story began just a few 100 million years after the Big Bang. Their starlight, stretched by 13 billion years of cosmic expansion, had finally arrived, translated from invisible heat into a spectacular image. The sheer clarity was staggering, but the real shock was the galaxies themselves. They appeared more massive, more mature, and more structured than anyone had predicted. Models of the early universe suggested a time of chaos, with small, irregular blobs of stars slowly merging. Instead, Webb saw fully formed disks and spirals in the universe's infancy. It was like opening a family album expecting to find blurry baby pictures, only to discover clear portraits of thoughtful young adults. This powerful new time machine is not just showing us the cosmic dawn, it is revealing that the dawn broke faster and more brilliantly than we ever dreamed. The telescope's ability to dissect the light from exoplanet atmospheres, to sniff out the chemical signatures of water and methane around distant worlds, is next. We are no longer just counting planets, we are beginning to taste their air. What other foundational stories of our cosmos, written in this ancient infrared light, will we have to rewrite as this new eye continues its long stare into the past? There is a certain power in turning a defensive act into an offensive maneuver. For the first time in our planet's 4.5 billion-year history, a resident of Earth intentionally altered the orbit of a celestial body. In September 2022, a refrigerator-sized spacecraft named DART closed in on a tiny, distant world. Its target was Dimorphos, a moonlet no larger than an Egyptian pyramid, orbiting a larger asteroid called Didymos. This was not a mission of exploration but of deflection. With a final, silent command, DART sacrificed itself, slamming into the asteroid at over 14,000 miles per hour. The impact was a spectacular, calculated act of violence, a direct hit witnessed by a small CubeSat that had trailed behind to capture the event. The sole measure of success was a change in a clock. Astronomers around the world turned their telescopes to Didymos, meticulously timing how long it took for the tiny moon Dimorphos to complete each orbit. Before the impact, its circuit took 11 hours and 55 minutes. Afterward, the clock had changed. The orbit was now 33 minutes shorter. A collective sigh of relief and triumph echoed through the global scientific community. The experiment had worked. The kinetic impactor technique, once the stuff of science fiction blockbusters, was now a proven technological reality. This was humanity's first successful test of a planetary defense system. We demonstrated that we could, in principle, nudge a threatening asteroid off a collision course with Earth, using nothing more than the straightforward physics of a billiard ball collision in the void. The data from the impact revealed surprises that are just as crucial as the orbital shift itself. The plume of debris ejected from Dimorphos was far larger than expected, suggesting the asteroid is not a solid chunk of rock, but a loose rubble pile, a gravitational aggregate of dust and stone. This rubble pile structure means that the kinetic impact does more than just push. It creates a powerful, rocket-like recoil from the ejected material, amplifying the deflection effect. Every piece of debris tells a story about the asteroid's composition and strength, information that is vital for designing future, more powerful deflection missions. DART transformed us from passive inhabitants of a cosmic shooting gallery into active participants in our own planetary destiny. We are no longer simply watching the skies and hoping for the best. We have taken the first tangible step to ensure that the fate of the dinosaurs does not become our own. How does it feel to live in the era when humanity learned it could fight back against the universe, not with weapons of war, but with the quiet, precise application of a universal law? Every civilization that has ever looked up at the night sky has tried to read its story. This relentless drive to decode the cosmos is etched into our history, from the builders of Stonehenge who aligned massive stones with the solstice sun to the priests of ancient Babylon who mapped planetary motions onto clay tablets. Their initial goals were profoundly practical, creating calendars to plant crops and navigating vast oceans by the stars, but the quest always ran deeper. It was a philosophical hunger, a need to understand where we came from and what our place is in the grand scheme of existence. This journey of discovery has never been a series of random accidents. Each breakthrough, from Tycho Brahe supernova to the first gravitational wave chirp, was a single brick carefully placed upon a foundation laid by countless minds before it. The tools of this quest evolved from naked eye observation to the abacus, then to the telescope, the calculus of Newton and Leibniz, and now to planet-sized observatories and subterranean particle colliders. The true engine of progress, however, has been a willingness to let the universe prove our most cherished beliefs wrong. We built entire worldviews on the idea of an Earth-centered, static cosmos, only to have them dismantled by a wobbling star or a moon orbiting Jupiter. This collaborative effort spans cultures and millennia, a chain of curiosity passed from Babylonian astronomers to Islamic scholars who preserved and expanded Greek knowledge, to Renaissance thinkers and to the global teams of today. Our modern understanding of spacetime is not a finished monument but the latest chapter in this endless story. How does this long arc of discovery shape our identity? It reveals that our greatest achievement as a species may not be any single theory, but the enduring collective courage to keep looking up and asking why. We have traveled a long road from a daytime supernova to touching the sun. These 25 events are more than just a list of discoveries, they are a chronicle of human curiosity itself. Each one, from Halley's prediction of a comet's return to the first sound of colliding black holes, has chipped away at our certainties and replaced them with a more profound and wondrous reality. Our journey reveals that the universe is not a static stage, but a living, breathing, and explosive story, one where space and time are woven into a single, malleable fabric. This transformation in our understanding is driven by a powerful cycle of observation, theory, and innovation. We see something unexpected in the sky, we devise a new explanation, and then we build a new tool, from Galileo's simple telescope to the planet-sized Event Horizon Telescope, to test our ideas and push even deeper into the unknown. The overarching theme that binds all these milestones together is a profound sense of humility. With every answer we uncover, we are greeted by a dozen new and deeper questions. The nature of dark energy, the true story of the universe's first moments, the search for life beyond our pale blue dot, these are the new horizons that now beckon us forward. This journey is an invitation to see the night sky not as a distant ceiling, but as a dynamic and endless frontier. It asks you to look up and feel that same spark of awe that drove Tycho Brahe and Jocelyn Bell Burnell to realize that you are part of a species with the audacity to map the cosmos. Which of these celestial moments most reshaped your own view of reality? Share your thoughts below and subscribe to join us as we continue this never-ending voyage of cosmic discovery.